Good morning, good afternoon, or good evening, wherever you're located in the world. And thank you for joining us on Wednesday, the 16th of July. It's 10 a.m. here in Texas for the AMETEK Solid-State Controls webinar on what is a bridge. So as always, if you see on the right-hand side, there's going to be a chat bar. If you can type in the chat bar that you can hear my voice, that would be ideal because I don't want to be talking to myself for the next hour. So if you can type in the chat, whether you can hear me or not, it would be greatly appreciated. And that also allows everybody to join. So that would be cool. Thank you, guys. You can hear me loud and clear. That's always a good thing. So first things first, my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solidstate Controls, located in Houston, just south of Houston, actually, in Stafford, Sugarland area. I have 24 years in the industrial UPS industry, and I have been with AMETEK Solidstate Controls for 8 of those years. And I've worked with all the different UPS charger manufacturers that are out there. There will be a lag of around 30 seconds, 20 to 30 seconds between you hearing my voice and me seeing a question. As I always say on every webinar, Webinar Jam is the platform that we use, and it's got to process a signal that I am creating, turn it into Microsoft, iPhone, Android. It's got to do all that processing, send it out to the world. So that takes about 15 to 20 seconds. So therefore, when I speak, you hear it about 20 seconds later. So therefore, I see any questions that come in 20 seconds later. So if you can do me a huge favor, in the chat bar on the right-hand side, you can see there is a tab that says chat, and there is a tab that says Q&A only. So if you have a question during the webinar, please go into the Q&A only tab and put your question in there. That would be ideal. And then at the end of the webinar, I'll go through all the Q&A questions, and we'll go through one by one and hopefully explain or answer those questions that you have. Webinar Jam also has a panic button. So if something goes wrong and I see in the comments that you can't hear me or you can't see the slides anymore or something goes wrong, I can press the panic button, a new room will be created, everyone will be invited to it, and we will carry on as if nothing happened, allegedly. So it is there, but it hasn't been used yet. And also, a very popular question is, will the webinar be recorded? And yes, the webinar will be recorded. Webinar Jam records the webinar. And basically, if you signed up for it, if you're watching this, you did sign up for it, you will receive a link for the replay after this session has finished. And that replay, I think it used to be that you couldn't fast forward, rewind, or do anything with it. It was just actually like watching a new webinar. But I think they've changed it. But anyway, what London, our wonderful marketing girl, has put in the chat bar there, what she does is she takes that video and she converts it to an MP4, uploads it to the AMETEK Solidstate Controls YouTube site. And once it's on there, you can share it, pause it, fast forward it, rewind it, link to it. You can do whatever you want. Okay, it's out there in the public domain. And if you want to share it with your friends or your colleagues, feel free to do so. So that is the link that London has put in the chat bar. You can go there, and all of our webinars are on our YouTube channel. So you can go and watch. I think we've been doing it for 3 years now. You can go watch any of those videos for free without any issues whatsoever. And the last thing is, the webinar should last around about an hour. Depends how much I talk, depends how many questions I get, but that's usually how long the webinars last. Okay, and what we're trying to do today in this webinar is understand what diodes and IGBTs are, understand how each semiconductor works, discuss power flow, general operation of each semiconductor in each bridge design, go over what a rectifier bridge is and how it operates, and then go over what an inverter bridge is and how it operates. And we'll do some stuff in between as well. Okay? So, for AMETEK solid-state controls and for UPS technology, all of the power semiconductors that we use act like a switch. This is really an important concept to get into your mind. We don't use the semiconductor device to amplify or do anything fancy whatsoever. We send it a signal, it turns on, and then it turns off, whether we remove the signal or we have to do something special for SCRs. But it is just a switch. But unlike a switch, which has moving mechanical parts, and therefore for electrical use, there's going to be arcing between the two contacts whenever it opens and closes, which can cause oxidization and breakdown eventually. A semiconductor switch uses whatever the semiconductor layer is, which is usually silicon, but it uses that layer as the switch, and there are no moving parts. And so it's an instantaneous switch, and there are no moving parts. So you can see on the screen here, we have a DC source on the left-hand side, and we have a lamp on the right-hand side. And then in between, we have a switch, okay? And when the switch is open, I know this is basic electricity, but it's an important concept to get into your head. When the switch is open, no power can flow from the DC source positive all the way back through the lamp to the negative, so the lamp will be off, okay? Very important to understand. When the switch is open, no current can flow, the lamp is off, okay? And when the switch is closed, obviously, power can flow from the positive of the power source through the lamp and back to the negative. We have to have a circuit, okay? And we have to complete that circuit, and the lamp will light. Please bear with me. I know this is basic, but it will help you understand how semiconductors and bridges work. So the first semiconductor device we're going to talk about today is the diode, okay? And the diode is designed to only allow current to flow in one direction, and that is from the positive or the anode to the negative or the cathode, okay? You can see basically the shape of there is funneling the current down that way. That's the way I like to see it. And then I also like to see that there is this blocking point here, so it's not allowing current to flow that way. So that is the inherent properties of a diode. It allows current to flow when there is voltage that is positive with respect to negative, anode to cathode, okay? And as I said, it blocks current cathode to anode. That is just its inherent properties. Some clever guy way back in the 1800s or whatever it was came up with this device. Actually, I think it was the 1900s. But very, very useful device. And obviously, electricity is usually quite complicated because you can't see it. So most people try to use some form of analogy, and water seems to be the stereotypical analogy that we use for electricity, even though the two don't mix very well. But what is the mechanical equivalent of a diode? And it's a check valve. It's a valve that allows current to flow in one direction. And as you can see, if current flows from left to right, it pushes the flapper up, and it will allow current to flow through the valve to the other side, okay? But if current tries to flow through this way, the clapper will be forced closed, and this is then sealed, and no current can flow through the valve in the wrong direction. And that is exactly how a diode operates. So it is the mechanical equivalent of a diode is a check valve. Now, instead of a switch in that original circuit that I had, now we're going to put a diode. Everything remains the same. We still have our DC source. It's still positive here and negative here. We still have our lamp on the right-hand side, okay? But when we put a diode in this configuration with the anode here and the cathode on this side, remember, if the anode is more positive than the cathode, the diode will conduct. So positive electricity is allowed to flow through the lamp and gets back to the negative, completes the circuit, and the lamp will light. In this configuration, you don't have to tell the diode to do anything. If you put a diode in this circuit, the lamp will light. Okay? And then if we turn the diode round, we now have the cathode on this side and the anode on this side. So now the cathode is more positive than the anode, and this diode says, you're trying to force current through me when I'm not designed to do that. And it stops current flowing. So current cannot get back to the negative of the DC source, and therefore the lamp is off. We don't tell the diode to do this. There is no signal sent to the diode. It just does it due to its inherent properties in its design. Okay. Now, what happens, because DC tends to be relatively easy to understand, what happens if we put an AC source on the left-hand side? We still have our lamp here, and we still have our diode here. Okay, well, this is going to be quite interesting. Let's see what happens when we turn the AC source on. So if we turn the AC source on for the positive half of the sine wave, you can see that here the AC source is positive with respect to this side. That's what a sine wave is. It tells you one portion of a sine wave is positive with respect to negative, and then it flips over and goes in the reverse direction. So that means the anode is more positive than the cathode in this, for this portion of the sine wave here, okay? So it does allow current to flow. The diode says, yep, that's how I behave. My anode is more positive than the cathode. I will allow power to flow through to the AC source, and the lamp will be lit for this portion of the sine wave only, or this portion, or this portion, for the positive half of the sine wave, okay? But for the negative portion of the sine wave, this portion here, the source is now positive here and negative here. So it's trying to go to the reverse direction. And the cathode of the diode says, no, I'm a check valve. I do not allow current to flow in the reverse direction. So it blocks the current for the negative half of the sine wave. Okay? The diode won't conduct when the current flows cathode to anode. And a question that I ask everybody is, if we put an oscilloscope on the lamp here and we looked at it, obviously the sine wave going in is here and the output is this waveform here. And the question is this DC? And I've answered it on the screen. This waveform here actually is DC, because it is not going past this zero crossing, this 0 volt line, okay? The current is always flowing in that direction, okay? So it's direct current. It's only flowing in one direction. If you looked at the sine wave above, we've got current flowing in that direction for the bottom half of the sine wave. So this is actually DC at the bottom here. So this circuit that is on your screen now is classed as a rectifier. A rectifier's definition is it changes AC into DC. So AC into DC, okay? And there are many types of diodes that we use inside our rectifiers and in our inverters as well. This is what's called a stud mount diode, and basically what you do is you insert this side into a heatsink. You remove that nut, and then you insert it into a heatsink, put the nut on the back, and you clamp the diode down onto the heatsink, and the heatsink becomes live, and then you connect your cable there, and then the heatsink has a cable connected, and you've just created the circuit similar to what I had on the page before. And you can see on each of these devices there is going to be a symbol printed on the side, and if we zoom in on that symbol, you can actually see that it's telling you that this side here is the cathode, and the lead on this side here is the anode. So current will flow anode to cathode through that diode there. But please bear in mind that they come in two variations. Okay, so this is the anode, this is the cathode, but on this one here, they have reversed it. This is actually the cathode, and this is the anode. And I know that because there's this red sleeving here that usually means cathode, and I just know because I created this slide and I know the part number that this is a reversed diode. And that is the same for SCRs as well. You can get two flavors. One, the stud is anode, and one, the stud is cathode. And you also get this multi-pack version where this actually has two diodes in it. So this is terminal 3, this is terminal 2, and this is terminal 1. And basically we have a diode going that way there, and we have a diode going that way there. And we have a connection point in the middle. And this actually makes it easy to create a rectifier bridge using two of these modules you would need for a single phase rectifier bridge. But it's called a semi-pack. This one's from Semicron. It's just a pack that has multiple diodes inside it. So we had to explain a diode so we can then try and help you understand what an SCR is. And the term SCR stands for silicon controlled rectifier. And it's also another name for it is a thyristor. Europe and some of the rest of the world uses the term thyristor, which is just a genericized term like Kleenex. A thyristor was a manufacturer of SCRs, and it caught on, so they call them thyristors. But it isn't SCR. We still have our anode. We still have our cathode. So it is just like a diode. If you took this away, this gate lead away, it would be a diode. Okay? But this is the hugely important difference between a diode and an SCR. We now have a gate lead, okay? And that gate lead allows us to send a signal to this semiconductor device to get it to do something that we want it to do, okay? And that is to turn on. Well, what is the mechanical equivalent of an SCR? It's a bit more complicated than just a check valve. It's actually what I would call a special check valve. So you can see here, I have drawn this wedge at the bottom here, and that is the gate of this mechanical SCR. So as you can see, when the gate is off, you can see that it is blocking the flapper from being able to move. The flapper cannot move when there is no gate signal. So even if you did have the positive on the anode side and the negative on the cathode side, without a gate signal, current will not flow. The flapper cannot move, okay? And obviously, just like a diode, it cannot move the other way. The flapper is in the way. So while the flapper is closed, no current can flow in either direction. Okay, it's an open. It's like a switch is open and nothing will happen until you send a gate signal. And before I move on, if you remove the gate signal, all you're doing is you're saying, okay, you can now behave like a diode. You're giving the semiconductor, the device, the permission to be a diode. That's all you're doing. There's nothing fancy. There's no amplification regions. There's just nothing special going on whatsoever. You send a gate signal to an SCR. It says, okay, now you can be a diode. In other words, you pull this gate signal back, and therefore, if the anode is now more positive than the cathode, current will flow, just like a check valve. And if the cathode is more positive than the anode, no current will flow the other direction. Okay? All you're doing when you send a gate signal is saying, okay, now you are a diode. So once again, we're going back to that basic drawing. We have our DC source on the left-hand side. We have our lamp on the right-hand side. Okay? Now, pay attention. We have positive on the anode and negative on the cathode. So if it was a diode, this lamp would light. But because we have this push button here and the push button is open, this is our path from the positive through a current limiting resistor to the gate signal on the SCR. If we are not sending a gate signal, then remember, we're not giving it permission to be a diode, so it will be an open. Okay? And if we turn the DC source around and had positive with respect to negative, without sending a signal to the SCR, current can't flow. We're not giving it permission to be anything. It's just an open. The switch is open, okay, with no gate drive. Now, if we close switch 1 and send a signal to the SCR, and the DC source is positive with respect to negative, current will flow and the lamp will light. It's saying, okay, I now give you permission to be a diode. But here's the interesting thing about an SCR. Once you give it permission to be a diode, it says, okay, I'm going to be a diode for the rest of my life until something specific happens. So you can see here that we've actually removed the gate drive signal. Current is not flowing through this resistor to the gate drive. We have opened this switch, therefore we have no gate drive anymore. But because we gave this SCR permission, we still have positive with respect to negative. The inherent properties of an SCR says, okay, once I am on, I will stay on as long as my anode is more positive than the cathode, or as long as my current flowing through my device is above what is called the holding current of the SCR, which is stipulated on the data sheet. So basically in this situation here, because this is a DC source, the current is going to remain flowing through that SCR for eternity, or until this DC source, if it was a battery, for example, drains all the way down to 0. Okay? If it drains all the way down to 0, that means the anode is 0 and the cathode is 0. No current is flowing through the SCR and it will switch off. Or what we can do is we can force it to switch off by inserting a switch. And we could open that switch. Current will stop flowing through this SCR. If current stops flowing, then it returns back to, okay, now I need permission to become a diode again. Okay. Hopefully that makes sense. And you can tell the difference between an SCR and a diode, because on an SCR, there is always leads coming off. So this one here is a hockey puck diode because it resembles a hockey puck. And there are a positive an anode and a cathode lead coming from there. This is one of the stud mounts similar to the diodes that we had, and you can see that there are gate cathode leads coming off there. And even on this multi-pack here, there is push-on connectors here, which are the gate cathode connectors, and they're here also for the SCR. So the SCR, you can tell the difference between an SCR and a diode because an SCR has the control leads or the gate leads going to them that need to be turned on to give it permission to be a diode. So that's diodes and SCRs. So now we're going to talk about transistors, and the transistors of choice in the power electronics industry are called IGBTs, which is an insulated gate bipolar transistor. Okay. And on the screen there, you can see two different drawings. They're both correct. We have a gate, we have a collector, and an emitter, and it's exactly the same on both. Okay. This one on the left-hand side is the most basic drawing you can get. We send a signal to the gate of the IGBT, and this is where the insulated part comes from. You can see that there is no connection between the gate, collector, and emitter. The gate is not electrically connected to the collector and emitter. Okay. That's the insulated part. On the right-hand side, they've drawn a circle around it. That's just how some people draw transistors. And they've also added this diode. Now, most IGBT manufacturers have a diode inserted in the manufacturing process of the IGBT. Okay, you don't add the diode. It's actually inside the whole package. And that diode is there for a reason. It's there if there is any inductive kickback when you switch, whenever you switch a switch on or off, and there is inductance, there is going to be an inductive kick in the reverse direction. Okay, especially when you switch a device off. That sudden stopping of current through any inductive network will cause a back EMF. And what it allows it to do is basically that will become positive with respect to that. If originally we had positive current flowing through the device that way. And then what that the diode allows us to do is get rid of that inductive kickback. What happens is we have a capacitor back here, and it allows the system to self-discharge that kick into our capacitor bank rather than destroy the IGBT, which can happen. So that's why the diode is inserted by the manufacturer to prevent inductive kickbacks from damaging the IGBT. Okay. And the circuit equivalent, I'm not using water in this circuit equivalent. Basically, it is as simple as having a spring-loaded switch, okay? And if we don't send a signal to the gate, in other words, if we don't press it with our finger, the collector and emitter is open. The switch is open, okay? It really is as simple as that. We're not using the transistor as an amplifier. We're not using it in any fancy region or fancy method whatsoever. We send a signal to it, it is closed. We remove the signal, it is open. Okay? Actually, let's go back. So when we do press the button, the contacts make and the collector and emitter are connected. So it is now closed. And because it's a spring-loaded switch, if we remove our finger once again, the switch opens. And unlike an SCR, the connection between the collector and emitter open as well. So the benefit of an IGBT is we send it a signal, it closes. We remove the gate signal, it opens. We don't have to wait for the zero crossing point. We don't have to wait for there to be no current flowing through it. We have direct control over the gate, whether the collector emitter junction is open or the collector emitter junction is closed. Okay, that is a big distinction between an SCR and an IGBT. So once again, here is the same circuit. We've got a DC source on the left-hand side. We've got our lamp on the right-hand side. And we have the same gate signal. We've got this switch here, which is open. We've got this resistor going to our gate of the IGBT. So if the gate is open, the transistor is off or open, and no current can flow to the lamp, so the lamp is off. And then when we push this button down, we send a signal to the gate of the IGBT, and we says, okay, you are now closed. You are now basically a short circuit in this diagram. Current will flow through the lamp all the way back to the negative of the DC source, and the lamp will light. Okay. And then if we remove the signal once again by lifting our finger off that switch or whatever is controlling that switch, and it went open again, then the lamp would go off. No current would flow to the gate, or no voltage would flow through the gate, should I say. And that means this circuit is no longer closed. The IGBT would be off and the lamp would be off. Okay. Just like this diagram here. We've gone back to the state where the switch is open, no current can flow through this IGBT because it doesn't have a gate signal. And this is two versions of what an IGBT looks like. And once again, if you look carefully, there are two IGBTs in this package here. And it's difficult to tell on this side. There's also two IGBTs in this package. And you can see that they have drawn the diode on each of the IGBTs on the side of the package there as well. Okay, so for this system here, okay, if I look at it correctly, this is the emitter, this is the collector. And so let's say that's IGBT1, and then this is IGBT2. So this is the emitter and this is the collector. Okay. And then it's difficult to tell because there is a brass ring around these two terminals, but there is actually two terminals. And the reason the brass ring is there is because IGBTs are extremely sensitive to electrostatic charge. And if you are handling IGBTs and you have an electrostatic charge and you touch the gate collector junction here, sorry, gate emitter junction, my apologies, you can damage, quite easily damage the IGBT gate, and it will not work anymore. So when the IGBT is shipped, it will have a brass collar or something to short the gate emitter junction together. But you can see this one here on the right. You can see you would just have a push-on connector, and one of these is the gate, and the other one is the emitter junction. Okay. So that is the devices that we use in a bridge. So the question that we have on the screen is, what is a bridge? And unfortunately, I am not Mr. Know-it-all. I rely on Google and AI just like everybody else, because I was thinking to myself, why actually is it called a bridge? So I did a search, and guess what? Couldn't really find anything of why it's called a bridge. I like this picture, though, because for those who know me, I am from Scotland, and this is the River Forth. This is the Forth Rail Bridge. This is the old Forth Road Bridge, and the one at the top is the brand new bridge over the River Forth. Beautiful area of the country in Scotland. But I digress. So I couldn't find really where the term bridge came from, but it was something to do with taking an electrical circuit and splitting it up equidistantly. It didn't really make any sense to me. The way I like to see it is it's a bridge between AC to DC or from DC to AC. Okay, that's actually what a bridge is. It's a way to convert AC to DC or DC to AC, a bridge between the two. So this is a half wave rectifier bridge, and it's quite self-explanatory. It's very similar to that original drawing that we had of a diode. Instead of a lamp, we have a resistor, and we are monitoring the output with our oscilloscope here. Okay, and this is the input to our rectifier bridge transformer here. Okay, so we are putting AC in. Now remember, with AC, current flows in that direction, and then current flows in that direction, alternating current. Okay, that's what you have to get used to with AC. It's not the amplitude. Yes, the amplitude is changing, but the amplitude is always positive for this portion of the sine wave. Although it changes size, it's always in the positive direction. And for this portion here, it is always negative. It does change how much voltage is flowing, but it is trying to drive current, but it is all in one direction for each half cycle. Okay, that way and then that way. I hope you understand that. So therefore, this is more positive than this for this portion of the sine wave. Okay, so if we follow the flow, our anode is more positive than the cathode. So yes, we can get back to our negative, which is on this side of the transformer here. So we do allow the whole of that top half of the sine wave through. Okay, but for this portion of the sine wave, this is now more positive than this. So current tries to flow backwards through the cathode to the anode. And the diode says, no, I don't allow that to happen. So this portion of the sine wave does not get through. So, as I mentioned before, is this DC? You should all be shouting at the screen now and saying, yes, Craig, it is DC. And that is correct. It is, because the current is flowing in one direction. It is now direct current. So that is the most simple, should I say, rectifier bridge. Now, it doesn't make sense to only half wave in most cases because you're wasting half of the sine wave. So some clever guy came up with a full wave rectifier bridge. And what they've done is they have put 4 diodes in this arrangement here. And now we have our sine wave going in. And what we're going to do is we're going to use both sides of the sine wave. So for this side of the sine wave and for this side of the sine wave, remember the current is flowing this way here. This is more positive than this. Okay, so if we go up to this junction here, can we go down this way? No, because that cathode says, I'm not allowing that to happen. Okay, it says you can't go that way. We have an anode here. We're funneling the current this way here. So yes, you can go this way here. Once again, we have a cathode. We can't go back down that way. So we go down through this resistor. Now, here's the bit that confuses some people. Now we have 2 anodes. So in theory, both of those diodes could conduct. But remember, it's positive with respect to negative. We have to get back to the negative from this point here. And this diode takes us back to the positive. So that does not conduct because we don't have positive with respect to negative on the anode cathode. But you can see here, that is connected to the negative. So we do have positive with respect to negative on this diode. So it does flow through that way. And that is how we get our positive half of the sine wave. Okay. And then here's the clever part. This negative portion here, now positive with respect to negative. So cleverly, we go along this one here because this is now more positive. We can't go that way because there is a cathode stopping us, but we can go up this way. And that gets us up onto the same line as the previous sine wave. And then it goes down through the resistor. We don't go up through this one because that returns us to the positive. But we do go down this one here back to our negative. And that flips this negative portion here and here back up above the 0 volt line. So we are now full wave rectifying the AC in. So the AC in, we now fully rectify that, and we're getting both portions of the sine wave on the output. So this is what we call a single phase diode bridge. Okay. And I forgot that I used a PowerPoint presentation to show you the power flow. So I'll leave that up there for a moment. The positive only flows in that path there. The blue diodes do not conduct. And then for the negative half of the sine wave, the blue diodes conduct and the red ones don't. Okay. Now, remember, we don't have control of those diodes. The diodes, all they care about is my anode more positive than the cathode? If so, I will conduct. There's no switching involved. Okay. So therefore, the input voltage directly affects the output voltage. And this is important. We'll get to it in a minute. So if we had 120 volts AC going in, the peak voltage is 170 volts. Okay. And there is a calculation that you use to calculate what the average voltage of a diode bridge is. And the average voltage, this here calculated, is 2 times the voltage of the peak. So that's peak to peak voltage divided by pi. And that works out to 108 volts. Okay. For a 120 volt input. But remember, all of our chargers are supplied by grid power. And we do not know what the grid is going to send. We do not know what your transformers in your plant are set at. We don't know if they're running slightly high, maybe 500 volts for a 3-phase system, or maybe slightly low, 460 volts for a 3-phase system. So if the voltage goes up, down, should I say, and your AC went down to 100 volts RMS, the peak is now 142 volts. So the average has now gone down to 90.4 volts DC. Okay. So previously it was 108 volts. Now the average has gone down to 90 volts. We have no control over that. That's what the grid is doing. So the output follows the input using this calculation. And if the output went up, the same would happen. If it went up to like 140 volts, then the peak would go up to maybe 200 volts, and that would work out at maybe 130 volts. I'm not sure. I don't know the calculation. Okay. So the way that we get around it, so the way we can actually control the output of the bridge with respect to the input is by inserting SCRs. And we can have 2 SCRs, so we can tell the SCRs when to turn on in each of the half cycles, and therefore we can regulate the output here. So you can see here we turned the SCR on at this point here, which correlates to this point here in the input sine wave, and it allowed this portion of the waveform through. And then we turned it pretty much on at the halfway point. So that was at this point here. So we allowed that portion of the waveform through. At this one here, we turned it on really late in the cycle at that point there, and we only allowed that portion through. And then for that final portion, we actually turned it on really early in the sine wave and allowed that whole portion through. Because remember, an SCR is just a device that we can send a signal to say, hey, you're now a diode. So when we have positive with respect to negative, anode to cathode, and we send a gate signal to it, it says, okay, now you are allowed to conduct. So therefore, that allows us to change the average on the output. Now, it's a very complicated equation to do that. But if you did a mathematical average of these areas under the curve, it would probably go high here, low here, really low here, and then high again here. So we can adjust the average out of that rectifier bridge for varying inputs. So therefore, if we have a battery connected to the system, and that's what most rectifier charges are for, is to charge a battery, is for varying AC inputs, we can keep the output constant at whatever level we want. Okay? And just to reinforce what we just explained, we've got our AC waveform going in. We turn this switch on at this exact point here in the sine wave. That means we have positive with respect to negative for the remaining portion. It will allow the circuit to conduct, and you will get this portion of the waveform on the output if you attached an oscilloscope between this point here and this point here. Okay. And what I wanted to show you is a little bit what would happen in the previous examples. So if we had low input voltage, so I said this was a 100 volts AC RMS input, we're going to turn the SCRs on pretty much at the midway point to get an average voltage that would look like that. Okay? If we calculated it mathematically. But if we had normal, this is 120 volts, I know you can't see it very well, but we're not turning the SCRs on as soon in the cycle. Look, we'll go back here, go back there. You can see, so now the mathematical average goes down. Okay. And even more so if we have a high input voltage, you can see that we're switching the SCRs on really late. So the mathematical average is even lower. So it shows you that we can adjust the output voltage with respect to the input voltage using SCRs. You can't do that with diodes. And then what can fill in the gaps? Because if we are charging batteries, we don't want this waveform to get to the batteries. And in truth, we don't want this waveform to get to the batteries. We have to find a way to fill in these gaps in between the waveforms. And what we use is an LC circuit. So it's an inductor and a capacitor. The inductor is in series with the load, and the capacitor is in parallel with the load. And this slide here shows you if you put this rectified output through this filter, this would be the filtered output that you would get. So basically, we have filled in the gaps. Remember, an inductor resists a change in current through it, and a capacitor resists a change in voltage across it. So the natural behavior of these two devices basically fill in this gap here. Okay, that's what it's doing. And if we went back to, I think it is this waveform here, and if we put the capacitor circuit an inductor circuit in there, what we're doing is, and this is hard for people to understand sometimes, the actual rectifier is only working for this portion here, okay? What it's doing at this portion here, it's supplying power to whatever the load is, and it's charging the capacitors back up. Then, from this point onwards, the capacitor does all the work until the next portion of the sine wave comes through. So if you looked at the input current to the rectifier, you would see a peak here, and that is the only time the rectifier is supplying current, okay? It's very peaky. The capacitor is doing all the work. The capacitor and the inductor are doing all the work in between the waveforms there. So when you look inside a system and you see plastic capacitors, and you think they're not doing anything, they're actually doing a lot of work. They're switching, they're filling in the gaps. And a three-phase bridge is 360 times in one second, sorry. So they are working hard all the time. And that's what the whole circuit looks like together. AC in, through the bridge. This is roughly here what the output would look like for a diode if this was an SCR. And this is what it looks like inside one of AMETEK solid-state controlled rectifier bridges. We've got a three-phase bridge, A phase, B phase, and C phase, and the paths are always with one with respect to the other. So let's do A phase with respect to B phase. So that's positive with respect to B phase being negative. So we would go here, we would flow through that SCR, through the inductor. Look, there's our capacitor there, and we would get back to the negative this way here. Now remember, we have to get back to B. That's this point here. So the SCR that we would use to get back is this SCR here. Okay? And that would give us one pulse on the output. Now, if we wanted to get B to C, B is more positive than C. B would go along here, get to this point here. There's the anode. We would go up this way through the inductor. There's a capacitor there, back down this way. And we need to get back to C, which is this point here. So we would go back up through here and back over there. Then the last one I'll do is C to A, more positive with respect to that. We would go along here. It would get up this way here, through the capacitor, back down. We have to get back to A, which is this SCR here, and we go back up there. So that is how the rectifier bridge works. And that is what it looks like inside one of our systems. A phase, B phase, C phase, okay? So that is our AC into the bridge. Here is our SCR pack, okay? One for each phase. And it really is as simple as there is AC going in on the left-hand side through these three bus bars here. And then these two bus bars here are positive and negative. So it's AC in, DC out. Okay, and there's our gate leads going to the SCRs. But that really is as simple as it gets. That is how a rectifier bridge works. Now, obviously, there's control boards involved and everything, but that is as simple as it gets inside our system. Whew, I'm talking a lot. We need to get through this. Let's move on to transistors or IGBTs in an inverter bridge. An inverter changes the DC back to AC. So here is our bridge. We call this an H bridge because it looks like an H, if you really use your imagination, okay? And we have 4 IGBTs, okay? So let's see how this works. So this is the same drawing roughly. Remember, we've got 4 IGBTs, and I told you at the very start, our IGBTs are acting like switches. So remember, H. We move to this one here. Look, we have an H. And instead of IGBTs, we now actually have switches. So here's S3 and S4. And in this picture, S1 and S4 are closed. This is our DC source. And we have a DC motor here. And if we make this side of the motor positive with respect to this side, and we do that by closing S1, which makes this positive, and then S4, which makes this side negative. That makes the motor spin in the clockwise direction. Okay? And then, if we close S3 and S2, and obviously open S1 and S4, magically, we haven't changed the DC. The DC is still positive in the top here. It goes through this switch. So this side of the motor is now positive, and this side of the motor is now negative. And that makes the motor spin counterclockwise. So we can now basically change the direction of this motor. So instead of changing the direction of the motor, what we want to do in an inverter bridge is change the direction of the voltage. So remember, we've got our DC source here, we've got our gate drive removed, no current to the gate, no signal to the gate, sorry. The IGBT is off. So if we measure on the output of the system, we don't see anything, okay? But when we send a short signal, when we push this button momentarily, the IGBT turns on momentarily, and then what we'll get is this square wave, and that will be at the voltage of the DC source. So if this is 135 volts DC, which most stationary plant batteries are, then the peak of this voltage will be 135 volts DC too. Okay? But we use PWM in our modern UPS systems, okay? And what that means is we can adjust the width of each of these pulses, which in turn adjusts the width of the off pulse, okay? And you can see in this waveform here, similar to the rectifier circuit, if you took a mathematical average of this very thin pulses, it will have a low average voltage. But if we widen the pulses here, and the off pulses are much, much shorter, the mathematical average of those pulses is higher. And that is exactly what we do with our IGBTs, okay? We turn them on and off, but we do it in a way where we start off with thin pulses. So look at this diagram here. We start off with very thin pulses, and then we move towards very fat pulses in the middle, and then it goes back out to thin pulses. And the mathematical average of that, very, very roughly, is a sine wave, okay? And the way that we do this is the positive half of the waveform. We switch IGBT pair A on, and you can see the current flow. Flows that way, makes this side of the transformer positive with respect to this side, okay? So we get these positive train of pulses. Hopefully that makes sense. And then all we do is we switch the B pair on. Remember, this is coming, we're not changing the polarity here. This is still positive and negative. But what we've done is if we follow this down, we've now made this transformer positive here with respect to negative. Remember, the previous one, this was positive. Now this is positive, and we get back to negative through this IGBT here. So that gives us our bottom half of the sine wave. And if we put the two together, you get this. And then all we do is we add an inductor and a capacitor, which you see there's an inductor here and a capacitor here. Usually the inductance is built into the inverter transformer now, but that fills in the gaps and actually makes a beautiful sine wave. Okay. And this is actually what it looks like in one of our rectifier bridges. So pay attention to the numbers. We have number 10 here is the positive, and number 12 here is the negative. This is going to be important because the next page I show you what the bridge actually looks like inside one of our systems. So we turn Q1 and Q4 on, and there's our inverter transformer here. So let's follow the power flow down. This is on. It goes down onto this connection here, goes out this way, and it makes this side of the transformer positive, and then this transformer gets to the negative through Q4, back to the negative. So that is negative, okay? And then we turn Q2 and Q3 on. Positive here, negative here, that does not change. We go down here, down to this connection point. We go up, and it now makes this side of the transformer positive, and this side of the transformer goes all the way down through this transistor here and gets to negative. So we are flipping basically the motor direction or the transformer field every 60 times a second, basically. But we do it 8,000 times a second in PWM, okay? And this is what our bridge looks like. Look, number 10 is our positive going in. Number 12 is our negative, okay? Our IGBTs are actually up here behind these capacitors. You can see this white device here. That's our IGBTs, okay? And we can see 21 and 16. If we go back here, 21 and 16, 16 there is the input to the transformer, okay? So we've got positive and negative going in, and we've got 21 and 16 going out. So it's DC going in and AC out. That's as simple as the inverter bridge gets. Phew, 2 minutes over time. That's not bad for me. So hopefully that explains what an inverter bridge and a rectifier bridge does. I'm going to go into our chat and our Q&A session. We have no questions just now. So what I'll do is some housekeeping. London has put in the chat bar here that the presentations will be provided after the web. They will not be provided after the webinar. That's a very common question. Do we supply the presentation? No, they are proprietary, but you can share the videos. And if you see there, London has put the link to our YouTube channel, and this will probably go live later on this afternoon, if not tomorrow morning. Okay. And also, you will, because you registered for this webinar, you will receive a survey. One of the questions in that survey is, what would you like us to discuss on our next webinar? Please do fill that out. I read every single one of them, and I'm looking for very good information on what I should present on my next webinar on. So I read every single one of them, and if there's something to say, oh yeah, that's an interesting subject, I will definitely use that to create a new webinar. And also, London has put in there, if you do want to contact us, you can go to our website using the contact page. You can email us. The email is going to be in the chat bar as well. And you can even pick up the phone and call us. We will answer, believe it or not. And somebody said we'd use SCRs for our inverter. Yes, in our old analog systems, we do use SCRs in our inverter, but it is a much more complicated circuit that is out with the scope of this type of bridge. It would have really muddied the water if I had discussed our SCR inverter bridge. But don't forget, we do offer training at our facility in Houston. And if you want to know more about analog inverter bridges, a prime time to do that is our nuclear class, which is in, I think it's December this year, and we go over our whole analog system and how it works. So go to our website, go to the training tab, and you will find where you can register for that class. Okay, let me see. I think we do have a question. The reason the inverter transformer is able to induce a voltage into the secondary because of the rapid switching. It is one of the reasons, Tanner. Yes, an inverter transformer is a coil of wire, which is an inductor, which therefore has a back EMF when the inverter's IGBT is switched off. So yes, that is causing back EMF, but even a cable, just a cable running from the IGBT to the transformer has some inductance to it. Every wire has some inductance to it whatsoever. So it's not just the transformer that induces the voltage back. It's cabling itself. And that is why we actually have what we call our laminated bus. So you can see our IGBTs are here, and there is no wire connecting the DC to the IGBTs. We use a copper laminated bus. And it's difficult to see here because number 10 actually has a plate the same size as the plate that you can see visible here. And it is separated by transformer paper. And we have a plate here and a plate here. And two plates separated by an insulator become what? I hear you all shouting. A capacitor. So not only do we have all these capacitors here, we also have capacitance built in here. So we're reducing the equivalent circuit inductance in our bridge to as low as we possibly can, because that improves the efficiency of the IGBTs, because we don't have the switching losses associated, because you have to slow down the switching if you have higher inductance. Hopefully I didn't confuse everybody with that. But that's a good question, a good statement, Tanner. So if we have no further questions, I hope everybody enjoyed that presentation. I hope you learned something. You know, I do speak a lot. Sometimes I speak fast because I've got a lot of stuff to go through in a certain amount of time. So if it got a little bit confusing, go back to the YouTube site, pause, rewind, listen to what I said. And in truth, if you have any questions after that, shoot me an email at the email that London's put on the screen, and I'll try and answer those questions for you. But until next time, thank you so much for spending an hour of your time with me. I really, really appreciate it. You guys are so busy. You have so much other stuff going on. And for you to choose to spend an hour listening to me, that just blows my mind. Thank you very, very much. I hope you enjoyed it. And until next time, take care, everyone.